Good morning. Thanks for coming. I'm going to present the status of the 3D printed USD2 stellarator and the first electron beam field mapping experiments. First, I want to give you this piece that is the main piece in the development. This is 3D printed. Now, in this case, it's molded and casted with resin. So this is light and this is weak, but later, after casting, this is strong. You have only to take care not to save very much the piece. It has some remains of nylon powder, but okay, no problem. You can pass around. So while I'm presenting, you can observe the piece. First, I'm going to give some background, later the USD2 conceptual design, the engineering concept and design, later some pictures of the USD2 construction status, the electron beam field mapping experiments performed, the results, and finally the potential future launch of research and development. The work is performed with very low funds, so the importance of the development are the construction manufacturing methods developed and not the size of the device or, for example, the future plasma performance. We know that the geometrical complexity of stellarators is one of the main drawbacks of this type of devices. So to try to lessen these drawbacks, the objectives of USD2 are first to try to contribute to the development of new better construction methods for stellarators and also for our fusion devices. And better means faster methods, cheaper, simpler methods. Another objective is to try to accelerate the research and development cycle. And the cycle means from the conceptual design of a new experiment and later the engineering design. Later we have the results. From the results we have another conceptual design. This is a slow, at the moment, very slow process and cycle. For example, in ITER, perhaps 50 years. Now, I only to give only some tips. Later we will deepen in the matter. USD2 is a small 3 periods stellarator of about 2,050 to 60 millimeters major diameter, and the plasma volume is 10 liters. Only to say now that here we have the coil frame from here to here. This piece is the piece you have at the moment, and these are in red planar coils that are larger than the other. This to say about the central circular ring is important to withstand the forces. Some legs and other elements, and the size is only 850 millimeters major diameter. Here, this is the current status. We see one half period here finished, and the other, this one is the one that you have there to see. This part is the one you have. One important thing is that the design has been performed from the very beginning to be produced and manufactured this piece by 3D printing. It's not the same to design for 3D printing that has been thought from the beginning than to think for milling or another type of manufacturing. The conceptual design. The origin is this, that it's an quasi-isodynamic stellarator from German researchers. It was modified to have a straight section. This is a kind of mirror section. So it can have some advantages. And engineering advantages mainly. One advantage is that we have white core here because these planar coils can be tilted. So in the case of a reactor, in a case of a large device, the remote handling machine can go inside this large port. Another advantage is perhaps it is possible to have individual half periods that can be disconnected. So the maintenance of in the case of a larger device or reactor would be produced by changing this half period and introducing another half period new. Another potential advantage is space for possible innovative high power extraction methods. Here we have this space here, the planar coils that are large, and there are some reference of many people that have developed new and more innovative methods for power extraction. Engineering concepts. This is the most important thing. The combination of 3D printing and casting is not only 3D printing. Here we have a piece that is a test piece, and there are truss struts that these are bars, these are beams, and externally covered with a surface. And at the end, you fill with epoxy resin or another type of resin, fiber reinforced or not, you fill all the hollow volume here on the top, so you obtain a strong piece, a strong component. The cost of this piece is 700 euros. And after casting, it's split in some points here. So we can see, after splitting the piece, at these parting lines, we can introduce a vacuum vessel that is also twisted vacuum vessel. And at the end, with bolts and all the elements are 3D printed, you can see in the piece that the holes for the bolts, all the elements, so it's much simpler to produce this kind of piece. In the case of the vacuum vessel, it's a modular vacuum vessel, so we have a central strike section here, and the other car sections that you can disassemble with a flange. This is the central vacuum vessel at this point here, and this is a liner. A liner reinforced externally with epoxy resin. The construction of this liner is very simple because they are only metallic strips that are formed, simply formed on a form. And later you have this liner that is weak, so you have to reinforce externally with epoxy resin, another type of resin, with a mold that was also 3D printed. And there are some claws and attachments to avoid collapsing the liner. Another important thing in stellarators is the positioning of the different elements since they are complex. The solution taken here is to have the sliding of the support of the piece, the half period. Later you have a contact with 3D printing pieces that are here. These are stops that are 3D printed on the piece. And contact with the central circular ring. And this is important to have a central circular ring because then with a slight rotation of the different sectors, you can locate accurately all the different half periods without using very complex metrology systems. This philosophy is similar to some approaches used in remote handling, in jet, also in ITER and in demo. Some pictures of the construction status. This is a full period from here to here. This piece and this component are the same, but they are rotated by Stellarator symmetry. We observed a large helical excursion of this type of devices, and because of this, there are short and tall supports. In this case, we see one finished half period, the coils, and this is the half period that is not finished, and you have here, this piece exactly is the same piece you have there. The vacuum system here, and another vision. All is finished except the construction. The construction is at about 25% completion. These are some pictures about the electron beam field mapping experiments. So here is an electron gun that's supported through an oscillating rod. Here we can see this is the fluorescent screen. We can see also a camera and a mirror here. This is a mirror, and you can see from the camera to this point to see the position of the electron gun that is inside this part. Some few words about the experiments performed by electron beam field mapping. This is a sketch of the system. It's the same as the photo. Here is the camera, here is a mirror. From the camera you see the mirror, you see the electron gun through this transparent window. And here is a fluorescent screen. It's the same as here. This is a frame from the recording. Yeah, this is the oscillating gun. And it's the same as this. This is oscillating through this point. And this is the electron gun that performs an arc, a movement like this. The movement of this electron gun is like this. It moves, creating an arc that is here in black. And these in red are the different orbits, different beams generated by the movement of the oscillating gun. The result are these fluorescent points at different points because the electron gun is moving to here. And this is the overlapping of these frames, that are frames from our camera. The result is here. In blue, this is the theoretical calculated intersection of the electron beams with the screen. And in cyan, these are the same points here, but are transformed due to perspective deformation of the image, because the camera is not perpendicular. We observe that the agreement of the experimental points that are in cyan with the theoretical calculation in blue is quite good. So we are quite confident that at the end, the stellarator, when we finish all the periods, will work quite well at least. This is not a very accurate system, but okay, it's enough. This is the video. You can observe here the point, and here the electron gun. The electron gun moves because this is a mirror, and this here you see the different points. Well, different points that move. Okay, it's clear? Well, the result. The manufacturing of the twisted vacuum vessel was time-consuming, so perhaps our methods, like for example electrodeposition or electroforming, maybe they would be better, at least for small devices. The accuracy of this piece you saw with respect to the design, the drawings, is only 0.3%, so it's still excessive and should be improved. The positioning strategy for the coil frames resulted satisfactory. A construction method for stellarator based on 3D printing plus casting have been developed. A method to fabricate a liner epoxy reinforced twisted vacuum vessel has been advanced. And the low cost, relatively low cost of up to now, the pieces produced up to now is about 2,040 and 400 euros. It suggests that perhaps the construction of a larger stellarator would be cost affordable and fast to produce. Potential future lines of research and development. Well, two alternatives for the future is the combination of metal 3D printing with metal casting. Perhaps titanium shell similar to the process followed in nylon, and later we could fill this with low melting alloys, zinc, aluminum inside, kind of casting. And okay, also the use of large laser 3D printers that are very recent. For example, this was sold in Beijing, in China, and it was produced in China. This is a piece for airplanes, and it's about 4 or 5 meters long. It's flat, but okay, this can would start to producing titanium in large pieces for fusion, perhaps for stellators, to Max, any. And what to print with this perhaps 3D printers or method? Well, also two options, A and B. One would be the production of a hybrid stellarator tokamak. This is one concept being developed in China also with collaboration with PPPL. And perhaps the possibility of 3D printing may allow to have 2 sets of coils, one for a stellarator and one almost for a tokamak. So we will have infinite intermediate configurations, and we could study the change from stellarator configuration to a tokamak stellarator. Another possibility is to use the new high beta stellarators being developed in Germany. This is quasi-ceramic stellarators of 6 periods with beta 9%, but perhaps could be 15%. That is very good. So, okay, with thick copper coils, 3D printed. This is another possibility. I like all of this, but this is very, very good also. And it's all acknowledgement to many people collaborating, references, and if you have any question.
Questions? Yes, please. Concerning casting, did you look at the investment casting?
Yes, investment casting is a bit similar to this because now a lot of investment casting, some investment casting is produced by molds produced by 3D printing at the beginning. So, okay, this alternative is somewhat similar. You can have lost wax casting and you are losing the piece. In this case, it would be a shell 3D printed, and later it would be doing a kind of casting. It's similar, yes.
Even if you don't print an X1 sells machines for printing the shell molds, but if you do just traditional investment casting, it's a very precise process offers the smallest tolerances.
Yes.
Yes. The shape is not that big, it looks like
yes, I would see that is, but okay, it's another alternative to produce components now at the moment. That is related with 3D printing, because you are producing the mold is produced sometimes. It is very complex with 3D printing.
You're not going to have that issue with distortion.
Yes, there is some small distortion, yes, and other thing here also. Yeah.
3D printing doesn't deal with that.
Yes. Okay, the errors obtained at the moment is 0.3%. And this printer was not the best in the world. It's an internet company in Netherlands. It's good, but it's not the best. Perhaps it could be 0.1%, but still it's a bit high for Stellarators, even for Topical Meeting. Yeah, thank you very much.
Any other questions, Dave?
What's the size of the effort? What is the size of the effort in this? It seems very forward-looking. I just wondered kind of the size of your effort. How many people or...
Yes, well, mainly myself. The other people have collaborated in some particular things. For example, explain me, Katya, how to produce this with Visual Basic. For example, the Nescoil. I made this with the Nescoil, but there's one people that went to Germany to learn, explained to me, okay. And the people that sent the different magnetic configurations, because I decided this from, for example, NCS, turbulent proof, and other configurations. So, well, the work 95% of mine, or a bit more even.
How long does it take to print? Is it complicated? How long does it take to print?
Well, it was printed in a company in Netherlands, it's Shareways, and I don't know because I asked them to print. Only I know the price, but perhaps less one day is half day.
Okay. Let's thank the speaker again.